All right. So again, good afternoon, everyone. This is lecture number 25 of IC242 Continuum Mechanics. But before we start, let's recap as to what we did in the last lecture, because it's been almost a week that we had this lecture. So lecture 24 was about differential displacements. We talked about writing differential displacement in terms of its symmetric and skew symmetric parts. I mean, differential displacement gradients, to be specific. We also talked about infinitesimal rotations, and we talked about velocity gradients. Okay, so doing a quick recap of what we did last time. So we talked about the relative differential displacement, that is du. So what we said was we have a point P, capital P, and we have a point small p, which is nothing but what capital P was in the deformed configuration. Then we have capital Q, which is a point around capital P, giving us a d capital X vector. And then we have a small q, which is the image of capital Q in the deformed configuration, which gives us a d small x vector. Right. So the displacement of point P is called u, and the displacement of point Q is called u plus du. Okay. That's how we define our relative differential displacement. So we said that arbitrary displacement can be a superposition of rigid body motion, which is translation and rotation, and deformation, which is what is that we're interested in this course. Then we wrote du in terms of its symmetric part, or the symmetric part of the displacement gradient tensor, which is called the infinitesimal strain tensor epsilon, and the skew symmetric part, which is what we defined as the infinitesimal rotation tensor. Okay, and that was the major topic of interest in the last lecture. The infinitesimal rotation tensor, as we know, is a skew symmetric tensor. It has three distinct components. So we were able to define a dual vector, that is omega tilde, using our omega kj. Okay, so this is how we define a vector which has three components using a skew symmetric tensor, which has three distinct numbers as its which constitutes this tensor. Okay, we then interpreted what this omega tilde actually means for our situation. So we substituted omega tensor, which is the infinitesimal rotation tensor, in terms of its definition of the skew symmetric part of the this displacement gradient tensor. Okay, so that told us that this was the curl of displacement u. Okay, so for a two-dimensional case, we tried to understand what this curl means, and what we obtained was that omega tilde is in the third direction. So this gave us some sort of understanding that omega tilde actually is the rotation vector that we have been considering in our rigid body dynamics till now. Okay, so but this omega tilde rotation vector actually comes from the infinitesimal rotation tensor, as we just saw. So finally, then we inverted. So we figured out a way to write omega tensor, that's omega ij, in terms of the omega tilde vector. This was purely a mathematical exercise. And finally, we were able to write, so in a situation where epsilon is 0, that is, there is no strain, we were able to write du, that's the displacement, differential displacement, relative differential displacement, only in terms of omega tensor, which finally then we substituted omega tilde here. So we were able to write the relative differential displacement du in terms of omega tilde and d capital X. And what we understood from here was it is simply a rotation, and omega tilde represents the d theta vector, which is a rotation vector. So this was all about differential displacements. Then we started talking about velocity gradients, because when we talk about fluids, it's not the distance the fluid has moved, it's how fast the fluid is moving. So we need information about velocity field rather than displacement field, because the fluid keeps deforming with time. And then we defined something called a velocity gradient tensor, which is similar to the displacement gradient tensor. So we wrote the velocity gradient tensor as a sum of symmetric and skew symmetric parts, and the symmetric part was known as the rate of deformation tensor. So remember, it was a deformation tensor in the previous discussion, and now when we talk about fluids, it becomes the rate of deformation tensor. The other part, which is the skew symmetric part, that is W, is called the vorticity or spin tensor. Okay, so the ideas were very similar to what we discussed in the previous situations where we had solids, where a solid was deforming into a deformed configuration. So finally, we can write L as a sum of D and W. The same way, we could write the displacement gradient tensor as a sum of epsilon and omega. In this, when we talk about fluids, in fluids, we don't have configurations such as initial undeformed and deformed configurations, because the fluid is continuously deforming. So we just talk about spatial coordinates in this case. So we only have small x1, small x2, and small x3. There's no capital X's here. I mean, we can have them, but there's no point including them. So here we have a point small p and a point small q. And the point small p has a velocity vi, and a point small q, which is around p, has a velocity vi plus dvi. So this is the definition of differential velocity dv. Okay, so that's so a point. So the point of interest here is still this p point, and everything around is all the points around p is what we want to understand, and then we would want to generalize the idea using the tensors d and w. So we write dvi, that's the differential velocity, as a sum of as a product of L and dx. Okay, so given if I supply dx, that is, if I tell you where this point, what the point q is, because for different dx vectors, because all of them originate from point p, different dx vectors just tell us where the point q is. So if I am able to tell you what dv is as a function of dx, then that's all we need. Okay, so we have the information about all the points around point P. So that gives us, all the points in the neighborhood of point P. Okay, so that was that's where we ended. So today we will continue with our discussion on velocity gradients, etc. We'll try to understand what's the physical interpretation of the terms of D, the same way we did in solids, where we try to understand what the different terms of epsilon mean geometrically. But before that, we will talk about something called stretch ratios. Okay, so we'll be talking about stretch ratio and the interpretation of the rate of deformation tensor D. All right, so let's define what stretch ratio is. Now let's go back to our discussion on the deformed and undeformed configurations. So remember, in the undeformed configuration, we had a vector d capital X, and in the deformed configuration, we had a vector d small x. This connects small p and small q, and this connects capital P and capital Q. So stretch ratio is the ratio of the lengths, that's the final length, to the initial length. So this is denoted by a capital lambda called a stretch ratio. Now again, a stretch ratio and all the, similar to all the other quantities are defined at a given point P. So the definition of lambda is specific to point P. But now you can have different d capital X vectors depending on where point Q is. So then lambda is also specific to n hat, capital N hat. So capital N hat, if you remember, is the direction of d capital X. So for different capital N hat, that is different d capital X vectors, that is different points Q, you have different stretch ratios. Okay, so the body may stretch different in a different way in different directions. So this quantity called stretch ratio, that is a capital lambda subscript n hat, is written as d small x by d capital X. Okay, so this the reason I'm talking about stretch ratio is because this quantity is important. It is used quite commonly in other discussions as well. So we need to understand and analyze this quantity further. So what we'll do now is we'll try to understand how we can write the stretch ratio in terms of the d small x vector. So sorry, in terms of the Green's deformation tensor. So what we'll do is we will take the square of dx for our analysis. So we start with the square of final length d small x. So this, as you know, in the initial notation can be written as the dot product of dxi vector with itself. So that's dxi. And I can write my d small xi in terms of d capital X using our f tensor, which was nothing but the deformation tensor. Right. Just recapping this. FIA is nothing but del xi by del capital X. This is the deformation gradient tensor. Now I'll just rearrange the terms here. So this becomes d capital XA. Then I can write FIA as the AI term of F transpose. And this F transpose F, as we already know, is nothing but our Green's deformation tensor, that is C. So this becomes CAB. This is DXB. So what I do is I'll divide both sides by d capital X squared. That's the length in the undeformed configuration. So the ratio of d capital X vector divided by d capital X magnitude is the n vector. Right. And d small x by d capital X is nothing but the stretch ratio, as we already have seen. So this can be written as the square of the stretch ratio, that is n hat dot c dot n hat. So we're still doing some algebra and understanding how we can write one in terms of the other. We are not using them yet. So don't get bothered with what is the use of this. We will definitely be using that later. But remember that the stretch ratio, the quantity stretch ratio, is quite important. It tells us how the body is deforming in different directions, or how the body is stretching or contracting in different directions. So lambda square is written as NCN, where n is the direction of the vector that we started with. So lambda will have different values for different n hat, as you can see. Now remember that C has nothing to do with direction. C contains all the information. So C, if you remember, was written, as you can see, actually is written in terms of F transpose F. And F, that's the deformation gradient tensor, contains information about all directions. Okay, so C tensor is specified at a point P. So if you take the product NCN, that tells you what the lambda value is for a given n. So as we change the value of n here in this expression, we get the stretch ratio for different n directions. All right. Now you may want to write everything in terms of the spatial coordinates rather than Lagrangian coordinates. So in that case, you can define a stretch ratio, that is small lambda in this case, subscript small n hat. It's again d small x by d capital X. So it tells us that it's stretching, but rather than specifying the initial direction, we specify the final direction. So what that means is if I go back, then this n hat is given as d small x vector by d small x magnitude. Okay, so if I know what the final direction is of the vector, I can define the stretch ratio in terms of that. So it's similar to the way we define everything in terms of spatial coordinates. Okay, so if I instead of starting with d small x, we start with d capital X here, the square of that. This again we can write as dxa dxa, and then you can write the let's use the symbolic notation. So this d capital X vector, if you remember, it's written as f inverse dot d small x, and this again is dotted with f inverse dot d small x. So it's again the spatial notation. And finally, when we simplify this, what we get is 1 divided by lambda is equal to small n dot small c dot small n. So small c again is a counterpart of the Green's deformation tensor. All right. Now the question is, are they equal? They become equal when your capital N hat maps with small n hat. Okay, so when I say maps with, that basically means that the capital N hat goes to small n hat. So in the undeformed configuration, we have a vector in the n hat direction at point P, and if that vector goes in the deformed configuration, that goes to small n hat at point small p, then we say that capital lambda capital N hat is equal to small lambda small n hat. All right. So let's analyze this a bit further. Now, you may remember the longitudinal strain that was denoted by E n hat. Okay. So that was nothing but the change in length upon original length. So that's called the longitudinal strain. That was the final length minus the initial length divided by the initial length. So the reason you have an n hat is because that denotes the starting or the direction of d capital X. Okay, so that's called the longitudinal strain, if you remember. So this can be written in terms of stretch ratio now. So we have this written as so the first d small x by d capital X is nothing but the stretch ratio minus 1. And we already have written the square of the stretch ratio, square of capital lambda as NCN. So this becomes equal to square root of NCN minus 1. So we have seen that we can link the longitudinal strain to stretch ratio using this expression. Now let's see what happens if we take capital N hat in a certain direction. So let's say that we are talking about the E1 direction. So in that case, our N hat is in the E1 direction. So if I take square root of E1 dot C dot E1, this is nothing but C11. All right, so this becomes square root of C11 because E1 dot C dot E1 becomes C11. Okay, you can write these in the matrix forms. So you can write E1 as 1, 0, 0. Then you can write C, then you can write again E1 as 1, 0, 0, and you will see that this is nothing but C11. Okay, and now we can also write that in terms of the capital E, which is the Lagrangian finite strain tensor. If you remember, the expression was C minus I was defined as twice of E. This is just a recall. So we can write this longitudinal strain in the even hat direction as square root of 2E11 plus 1 minus 1. Okay, so I've used the relation C minus I equals twice of E. So E twice of E plus I is C, and since we're talking about a diagonal term, then we have twice of E11 plus 1 is equal to C11. Okay. Now we can use this expression where we have the longitudinal strain in E1 hat direction written in terms of the Lagrangian finite strain tensor component E11. We can write E11 in terms of small e. So if I just move around the terms and square them, what I get is E11 is equal to E squared by 2 plus E plus 1. Sorry, I don't think we have a plus 1 here. Okay. So now you can see that we have been working with finite strain tensors here, not infinitesimal strain tensors. So now under the approximation that we have infinitesimal strain theory valid, that is, if your deformation if your deformation and deformation gradients are small, then what we see is that E square is much, much less than 1. So E is nothing but the longitudinal strain. So if everything is small, then the square of a small term is much smaller than the small term. So if we add them together, then we can write that as approximately. So E square by 2 plus E is approximately equal to E. And this was nothing but E11. So what we see is that E11 is approximately equal to E. And we also saw that E becomes equal to epsilon. And E becomes equal to epsilon when you have the infinitesimal deformation theory valid. So under the infinitesimal deformation theory, here this E becomes equal to epsilon 11, and that is approximately equal to E. But we already have seen that. There's nothing new here. We already have seen that the diagonal terms of the strain tensor epsilon, their interpretation is longitudinal strains. So there's nothing new. We just derived whatever we started with, except that in a slightly different way. Anyway, so this was just a recap of the previous exercises and reinforcing the ideas that the diagonal terms of the strain tensor epsilon, they denote the longitudinal strains in the component directions. All right. All right. So the next discussion that we'll have is we will talk about how the change in angles. So till now, the previous discussion that we had was about the longitudinal strain. Now we'll see how the change in angles between two vectors can be related to our stretch ratios. So what we'll do is we will take two vectors as we have been doing. So we'll take these small x1 and take a dot with d small x2. So if you want to get a picture of this, so you have a point capital P, and you have points Q and R, and these map to sorry. There was a big spider who jumped on me. Then we have points small p, small q, and small r. So what we'll do is we will take the dot between dx1 and dx2. So these come from d capital X1 and d capital X2. So this, in fact, if we divide that by their magnitudes, just saves a step. So this is cos theta, where theta is the angle between d small x1 and d small x2 vectors. Okay. So the idea is to be able to use stretch ratios here. So we will write cos theta on the left hand side, and the right hand side, where we have d small x vector, we'll stay with the symbolic notation right now. So this becomes f dot d small x1, and d small x2 can be written as f dot d small x2, and their magnitudes can be written as like this. So it's using the idea that the stretch ratio is NCN. So if lambda is NCN, then N is nothing but d capital X by d capital X vector by d capital X magnitude. So if you play around with them, then instead of NCN, you get dx c dx. So we have simply written using the stretch ratios here. Okay, now we can write this as d small x1 dot c dot d small x2. Sorry, I made a mistake here. This should have been d capital X. Apologies for that. So it's a d capital X here. And in the denominator, we have the same terms again. So now if we divide the numerator and denominator by d capital X1 and d capital X2 magnitude, so what we get is, so cos theta equals N1 times C times N2 right? So that's what we get if we divide both sides, both numerator and denominator by d capital X1 and d capital X2. And again, we can see that the denominator here is simply so you remember that NCN was lambda. So this becomes, well, NCN was lambda squared. So square root of NCN is nothing but lambda. So that's our cos theta. Right. So now in this N1 and N2, if I go back a slide, then capital N1 and capital N2 were so in the undeformed configuration on the top. Capital N1 and capital N2 were not taken perpendicular to each other. They were arbitrary directions. Now, if we take them to be perpendicular, in fact, if I take N1 as E1 direction, and I take N2 as E2, so let's assume that this is the case, then cos theta, we tend to write that as theta 1, 2, as we have seen earlier, and then E1 dot C dot E2, this, as we know, is nothing but C12. And the denominator, we have square root of E1 dot C dot E1, which is nothing but square root of C11. And then we have a square of E2, square root of E2 dot C dot E2. That becomes square root C22. Okay, so what we've done is we have written cos theta 1, 2. So remember that we took the initial directions capital N1 and capital N2 perpendicular to each other, that's E1 and E2, which we know are perpendicular to each other, they are component directions. After the deformation happens, so small theta denotes the angle between d small x1 and d small x2, and they may not be perpendicular. So this, so what we have done is we have been able to write our theta in terms of the c values here. So we use stretch ratio, the idea, and then we wrote everything in terms of c. So we haven't done that. We haven't used the interpretation of c till now, but in this discussion, that's what we understand. So it's been a long time we haven't discussed any example. So let's solve a problem and see how we can use these ideas to our purpose. So this is example number 481 from the textbook. That is Mace and Mace, second edition. So what it says is that we have a homogeneous deformation. Okay, with the mapping equations, which are given as okay, so we have a deformation which has the mapping equations small x1, small x2, and small x3 written in terms of capital X1, capital X2, and capital X3. So this is, I mean, you may remember that's the function chi, which helps us write the final coordinates in terms of the initial coordinates. So we've been asked to determine the stretch ratio Okay, so the first question is we have to determine the stretch ratio in the direction of n hat, which is given as E1 plus E2 by root 2. Okay, so that's problem, the part 1 of the problem. And part 2 is to determine the angle theta 1, 2. All right, so theta 1, 2 in this case is the angles, the angle between elements which were initially in the directions of n1 hat and n2 hat, where n1 hat is what's given in part A and n2 hat is E2. So remember that we have not assumed them to be perpendicular to start with. They are actually at an angle of 45 degrees to each other, as you can see. Yeah, okay, so let's solve this problem. So we will start with finding out the F tensor, that's a deformation gradient tensor in this case. So the F tensor, if you remember, that was nothing but del xi by del capital XA tensor. Okay. So f11 is del small x1 by del capital X1. So these are the equations. So in fact, I can write the f tensor here only. It will make my life a bit easier. So del small x1 by del capital X1, as you can see, that's 1. Then del small x1 by del capital X2, that's -1. And del small x1 by del capital X3, that's a 1 again. Okay, similarly, del small x2 by del capital X2 is a 1. Del small x2 by del small x2 by del capital X1, that's a 1. Del small x2 by del capital X2, that's a diagonal term, that's a 1 again. And the third one is a -1. Similarly, del small x3 by del capital X1 is a -1, and the rest two are 1s. So that's my deformation gradient tensor, or the F tensor. Now you can see that the F tensor here does not depend on x1, x2, and x3. So that's the reason it's homogeneous. Okay, homogeneous means it's the same everywhere. Since this F tensor does not depend on the x1, x2, and x3 coordinates, that means that this F tensor is, or the deformation is homogeneous. So don't confuse that homogeneous deformation means that our x1, x2, and x3, small x1, x2, and x3, they should not be dependent on capital X's. Of course, they have to be dependent because it's a mapping. But the deformation gradient tensor F, if that is independent of my capital X1, capital X2, and capital X3, that means that the deformation is homogeneous. Right. So we have an F. I'll just copy it from there. All right. So then I can find C. C was, if you remember, was F transpose F. So if I do that, well, I leave it for you to do that. So this becomes 3 minus 1, 1. So minus 1. Okay, so this is our Green's deformation tensor, or capital C. So let's start solving the first problem now. So we have to find the stretch ratio in the direction of n1 hat, where n1 hat is given as E1 plus E2 by root 2. Okay, so remember that stretch ratio, the square of that was n dot C dot n. So our n here is so 1 by root 2, 1 by root 2, 0. That's E1 plus E2 by root 2. Then you have your C tensor. Right. So it's simply a matter of this matrix multiplication, and when you do that, what you get is this is equal to 2. So that means your lambda, which is the stretch ratio in the n1 hat direction, is equal to root 2. Okay, so that was part 1. Now in the second part, we have to find the angle theta 1 2 in the deformed configuration between n1 and n2 vectors. Now let's go back to the discussion on theta 1 2. So we don't cos theta. So cos theta was written as n1 hat dot C dot N2 hat divided by lambda in the N1 hat direction times lambda in the N2 hat direction. I'll show you. That's what we coming from here. So I simply have copied this expression. So that's telling us what cos theta is for the angle for the d capital X1 and d capital X2 in N1 hat and N2 hat directions. Okay, so instead of superscript bracket 1, we have a subscript in n's in this case. Okay, that is just for representation. All right, so we simply have to substitute. So our N1 here is still the same. So that is 1 by root 2, 1 by root 2 and 0. And N2 is written as E2. N2 is given as E2. So that is 0, 1, 0. Okay, so we already know what C is. We know what N1 and N2 are. It's simply a matter of substituting these things and getting the answer. Okay, so when you do that, you get this cos theta as root 2 by root 6. That's nothing but root 1 by 3. So theta is 54.7 degrees. Okay, so you started with so the angle between N1 and N2 was 45 degrees. I mean, you can see that. So N2 is nothing but the E2 direction, and N1 is nothing but, so if this is your E1, this is your E2, then E1 plus E2 by root 2 is this direction. That's your N1, and this is your E2. So this angle was 45 degrees to start with, and now it is 54.7. Okay, so in the undeformed configuration, the angles between N1 and N2 are 45 degrees, and in the deformed configuration, the angles between d small x1 and d small x2 is 54.7 degrees. Okay. Now, just a couple of more minutes on the stretch ratios, and then I think we have to stop because we are running out of time. Now, going back to our expression for cos theta 1, 2. So let's go back and have a look. So our cos theta 1, 2 was written as C12 divided by root C11 root C22. Okay, so this is when your N1 direction was taken as E1 and N2 direction was taken as E2. So they are coordinate directions 1 and 2. So you're trying to understand how the angle between these perpendicular directions changes as the body gets deformed. Now, if I mean these directions that we are choosing, let us choose them in such a way so that they are the principal directions of C. So C is a tensor. C is a second order tensor. So let's choose E1, E2, and E3 as the principal directions of C. It's always possible, we can choose that. So when we do that, we already know that a tensor in its principal directions, or a tensor transformed into its principal directions, is a diagonal tensor. So C12 will be 0, right? So what we have done is we're trying to represent our C tensor in its own principal directions. So that means it's a diagonal tensor now. That means C12 is 0. So what that means is cos theta 12 is 0 because C12 is 0. So cos theta 12 was C12 divided by something. So this is 0. So that means theta 12 is pi by 2 radians. So what we see is that if you start with perpendicular directions E1 and E2, they stay perpendicular. So right angles remain right angles in the deformed configuration. Okay. Now I will leave it to you to show that the principal directions of C are the same as principal directions of E. That is your Lagrangian finite strain tensor. It's very easy to show, so I'll not go into those details. Now the reason we are doing all this is to be able to write um, the dilatation. So that is dV divided by dV naught. So this is dV denotes a small infinitesimal, a small volume in the deformed configuration, and dV naught denotes a small volume in the undeformed configuration. Okay, so these are given as d small x1, d small x2, d small x3. And using our stretch ratios, we can actually write them as lambda n1, lambda n2, okay, because d small x by d capital X is nothing but stretch ratio lambda. But remember that n1, n2, and n3 are the principal directions in this case. So if I try to write my lambda square n1 hat, it is nothing but n1 dot c dot n1. Okay, that's the definition of the square of stretch ratio. Now, since n1 is a principal direction of c, then c times n1 can be written as, so the definition of principal directions are that c times n1 is some constant which is the eigenvalue times n1. So this will denote by c1. So c1 is nothing but a number here times n1. So there's no dot here. So this becomes c1, and now n1 dot n1 is 1, the unit vectors. This simply becomes c1. So using these ideas, we can write our dv by dv naught as square root of c1, c2, c3. Now c1, c2, and c3, they are c1, c2, and c3, they are the eigenvalues of c, and we already know that the product of the eigenvalues is nothing but the third invariant. You can go back and check. So this is the third invariant. Now the interesting part here is that we can find the dilatation by simply taking the square root of the third invariant here. And remember that the third invariant of C is nothing but the determinant of C. You may not want to find the eigenvalues because finding eigenvalues is not a straightforward process. It's computationally expensive. So what we can do is we can simply find the determinant of C, and that is the third. That is this is nothing but the determinant here. That's the third invariant of C. and that gives us the dilatation in this case. So again, there's so many definitions that we have, things that we have defined here, and then after defining the ideas, we have understood them through through an example, and try to interpret what happens in special cases. So if you understand each and every step one after the other, then the bigger picture will get clear when we start using these things in greater detail. Okay, so we'll stop here, and if you have any questions, please feel free to ask.